All right. Okay, guys. Those of you guys who are Star Wars fans. All right, just go to hell. Let's talk about Star Trek. Basically, all right. In terms of the Star Trek term, so you got this Klingon spaceship. It's moving away from the Earth at this speed. So it's moving away from the Earth at 80% of the light speed. So this is the Klingon. It's moving away from the Earth at 80% of the light speed. And we got the Starship Enterprise. It's pursuing it at 90% of the light speed relative to Earth. All right. So what is the question? Okay, so the observers on Earth see the Enterprise overtaking the Klingon spaceship at a relative speed of 1/10 of a c. All right, but that's the difference in speed between these two. All right, so what is the speed that the Enterprise is overtaking the Klingon spaceship as seen by the crew of the Enterprise? All right, so with respect to us, it's overtaking the spaceship by 1/10 of the speed of light. But from the perspective of the crew, what is the actual speed with respect to them? So that's what we're going to be looking at. One of the things that you will struggle with, and this is the reason why you kind of have to practice this before taking the test and get used to identifying each and every single term, is knowing what's what. All right, so you have to be able to label things correctly. All right, so what do we know? All right, so this is 80% of the speed of light is the speed of the Klingon spaceship. All right, so we're looking at its speed relative to Earth in essence. All right, so this is the object whose speed that we're interested in. And then we're going to try to express its speed relative to this moving observer. All right, so this one is the one which is going to be moving at 90% of the light speed. All right, I'm not using the same terminology as, I don't know which book I got this from, but I changed the notations a little bit. All right, so this is our moving observer. Our moving reference frame is moving at 90% of the light speed. And this is the object which is moving with respect to this reference frame as well as that reference frame. So with respect to the Earth reference frame, this thing is moving at 80% of the light speed. So the question is, how fast will this be moving with respect to the moving reference frame, which happens to be that? All right, so just get used to identifying the terminology properly. So that requires a little bit of practice. All right, so the solution in this case is going to be, out of the two equations, we will get to use the second equation because we are interested in the speed of a moving object with respect to its second moving reference frame. All right, so that's the second equation that we have. All right, I decided to show a little bit more work because when you do this, notice that the units are going to be expressed in terms of speed of light, so that you're not wasting a lot of time by expressing speed of light in terms of meters per second. All right, just keep the speed of light as units, and you will notice that there's some easy cancellations, and the final answer is going to show up in terms of speed of light. All right, so from the perspective of the crew, they're going to be overtaking the Klingon spaceship at about 35% of the light speed. That's what it means. All right, so you may have to kind of practice identifying the terminology. All right, so now we got a similar problem. Okay, so let's take a look at what this is. All right, so we got two rockets, A and B. Okay, so they are moving at 90% of the light speed relative to Earth. Both of them are moving relative to Earth, and they're moving towards each other. All right, so calculate the relative velocity of B with respect to A. All right, so we got two spaceships, rockets, A and B moving towards each other at 90% of the light speed. So figure out the velocity of B relative to A. So that's what we will have to do.
Are they on parallel paths?
Okay, yeah, that's the assumption. Give yourself 5 points for that one. Okay, so let's take a look. This is something that I try to visualize. So I've asked, is there a reference frame? So this is a station reference frame, Earth reference frame. And then, so you got A, you got B, they're moving towards each other. All right, so A is moving, this becomes the reference frame, moving at this speed relative to Earth. And this is, we're going to be interested in the speed of this reference frame with respect to that, if that's the case. So it's moving in the opposite direction. All right, so station reference frame, this becomes our reference frame. All right, this is going to be moving at this speed relative to Earth. Okay, so I'm trying to identify things. All right, so our moving reference frame is going to be A in this case. All right, so this is our moving reference frame. This is moving at 90% of the light speed relative to Earth. And then we're going to be interested in how fast this thing is moving relative to that. Okay, and then I changed my mind. I was going to put a question mark. All right, and then the second reference frame is moving at 90% of the light speed relative to Earth, but notice that the direction is towards the Earth. So we'll put a negative there. And now we're going to be interested in the speed of this one relative to A. So that's the reason why we're using the prime term. Okay, once again, pick and choose the right formula. It's straightforward. So that's the formula. And then plug the numbers in. I'm not going to show too much work here. And it's going to be 99% of the light speed. It's kind of like the Star Trek problem, except this one is moving in the opposite direction. Okay, so I think we're done with transformations. Okay.
In order to simplify the problem he sees with light, Einstein uses a series of thought experiments that take place only in his imagination, like a journey on a train.
From James Clerk Maxwell's equations, we know that the light reflected from my face traveling toward this mirror must move at 186,000 miles per second. Okay, Einstein said, but what if the train were moving at the speed of light?
One possibility is the train catches up to the light waves, so they never reach the mirror. But Einstein is convinced this can't happen. Light can't stand still.
And what does it mean if I do see my reflection in the mirror? Well, from my point of view, everything is just fine. But for the person standing outside of the train, there's a problem. That person sees the train moving by at 186,000 miles per second, and therefore the light reflected from my face traveling toward the mirror must be traveling at twice that rate, or 372,000 miles per second.
372,000 miles per second is the speed of light added to the speed of the train carrying the light. Physicists have added speeds this way since the days of Galileo. But Einstein concludes this simple adding of velocities is wrong, because the speed of light never changes. It's always 186,000 miles per second, even if its source is in motion. Whether on or off the train, you have to get the same measurement for the speed of light. The stunning consequence of this is that someone off the train measures rulers on the train as short and clocks on the train as running slow.
In a flash of brilliance, Einstein proposes that distance and time are not absolute, that a foot and a second measured on the train are not the same as a foot and a second measured off. Distance and time are relative.
All right, let's make that transition. So if the light speed is constant, what would happen if we could travel at the light speed to New York City? What happens to space? In the direction of motion, when you start to approach the light speed, space is going to contract, right? All right, so it's going to contract to a point. Okay, distance divided by time should still give you the light speed, which means that the time also needs to go to 0, which means that the time is going to slow down. Okay, immediately Einstein notices that if everybody experiences the same light speed, space has to contract, the time has to slow down. All right, so this is known as contraction of space. So space is going to get smaller, and space is going to contract only in the direction of motion outside of your reference frame near the light speed, and it's going to contract by this much. All right, so this is known as the relativistic factor. All right, this is your speed relative to the light speed. So that term needs to be squared, subtracted from 1, and then you take the square root of it, and then you invert it, and it becomes your relativistic factor. All right, so which means that the length is going to shrink by that factor. It gets divided. All right, x is known as the proper length. X is known as the relativistic length. All right, so this is the first prediction. So the first prediction says the space is going to contract in the direction of motion near the light speed by this much, by the relativistic factor. So what's going to happen to time? Your time is going to slow down. All right, so the next one is known as the dilation of time. So which means that the time is going to become expanded, the time that you experience. All right, so time is going to slow down inside your reference frame near the light speed. All right, so TO, all right, this is once again the relativistic factor. This is your original time. So your original time is going to become expanded by the relativistic factor. All right, so TO is known as the proper time. You're the one who measures the proper time when you're moving near the light speed, and the T is known as the relativistic time. That's the time that we measure for you on a stationary reference frame. So we actually looked at some examples of that. All right, originally, about a week ago. All right, so light is always going to travel at the light speed relative to you, regardless of your own motion. Time is going to slow down in a reference frame traveling near the light speed. Space is going to contract, which means that it's going to shrink in the direction of motion outside of your reference frame. Once again, only near the light speed. Relativistic speeds means you're moving very near the light speed.
Hold on, we're taking off.
Fortunately, this phenomenon is only noticeable close to the speed of light. Imagine yourself alongside early 20th century science fiction swashbuckler Flash Gordon. When not fighting the bad guys or trying to escape from some monster, You're dashing around the galaxy at incredible speeds. While you are, your clock and those back on Earth are running at different speeds. Assuming you've been gone for the better part of a year, when you get back, everyone you knew would have been dead thousands of years. It's the ultimate example of relative time.
Okay, so we have actually seen this as well as the previous video, so I'm just gonna move forward. Okay, we've also seen this one as well. All right. Okay, so this is the proper time, and this is the relativistic time. So if you spent 10 years in space, we're going at 17,500 miles per hour. Obviously, you will age 10 years. Everyone else is going to age 10 years as well. And then you will start to see the time dilation effect when you start to approach the light speed. All right, so you spent 10 years in space moving at 90% of the light speed. Upon return, you will notice that it'll be about 22 years here on Earth. So people will be about 12 years older. 95% of the light speed, by the time you age 10 years, everyone is going to age about 32 years. And 95% of the light speed. 99% of the light speed, within 10 years, you can leap 7 years into the future. 99.9% of the light speed, within 10 years, you can leap 223 years into the future. 99.999% of the light speed, within 10 years, you can leap 700 years into the future. And 99.999% of the light speed, within 10 years, you can leap over 2,000 years into the future. And it goes on, guys. Very closer you get to the light speed, the more the time is going to slow down for you. That's what it means. All right. All right, so those are the examples of time dilation. Okay, do you waste thousands of years while you're slowing down? All right, hold on. You don't have to. You can accelerate at a rate which is 1g. It takes you about a year to actually get up to the light speed. And you can also decelerate at a rate that equals to g. So it's going to take you about a year to actually slow down.
There it is. That was weird.
No, that's fine.
Space flight may one day unlock the secret of time itself.
I believe in 50 to 100 years, we will in fact have rockets that will take us near the speed of light, ion engines, photon engines. They'll take us to the speed of light where time itself begins to slow down. One of the most preposterous predictions of Einstein's theory is that the faster a rocket moves, the slower time beats within that rocket ship. Imagine somebody taking off near the speed of light, and you're sitting on the Earth with a telescope. And as you look in your telescope, looking at the rocket ship, you see that everyone inside is frozen in time, because the rate at which time beats has actually slowed down. So we've actually measured this in the laboratory with atomic rockets, with satellites. We can actually measure the fact that time slows down the faster you move.
At any given second.
Here's what he's talking about. All right, so if you just televise live, this is something that we've seen before. Of these people who are moving near the light speed, their 1 second could be a minute long, hour long, 10 years long. So everything is going to look frozen.
In here, it's always Friday.
In their own reference frame, though, everything is going to look normal.
Boom, 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 boom.